place some numbers here for this one. Just in case I need the numbers to see what's going on here. And then I'll get ready. Label a few here. A few down here. And I'll get to that grid there shortly here. Now, before I jump into the grid and see what all this is about, let me go on the side here and ask with my description. All I'm doing is a description here. Number one, if I see bracket, I'm gonna use the brackets, guys. And inside here, I place a 1/2. I'm replacing x by 1/2. Translation. When I go to this set of integers, can I find 1/2? No. I know in real life, I know where it is. It's caught between 0 and 1. It is 1/2 caught between 0 and 1. Now, since I cannot find it directly in that set of integers, they want to know which one comes closest to it, not over it. How close can you get to it? And which integer in the black here would be the closest to 1/2? Which one could I accept in this set as the closest one I can get to 1/2? I'm not going to go over it. And I'll accept that as my greatest integer function. Yes?
2.
There we go.
Isn't it 2?
Not 2.
Oh, 1.
Not 1. I see why you said 1.
Okay.
I see why you said 1, not 1. What's the closest I can get to 1/2 and not go over 1/2?
0.
0. He tells me it's 0. Guys, right there, that number right there is the closest I can get to 1/2 and not go over. Well, it so happens, if that's correct with what he gave me, if I ask you what is the greatest integer function value for this? 3/4. You say, Professor, 3/4 is not in that set. But I know the location, it's also caught between 0 and 1. So it's in there somewhere. Now, what's the closest I can get to 3/4 of the black integers and not go over?
0.
Is it 0 again? So something strange is going on when I get to the graph. Some of these values are repeating. Number 3. Now let me write like this. What do you think the greatest integer function value at 5/2, which is 2.5? And I know 2 1/2 is not directly in that set, but I know in real numbers where it is, it's caught between 2 and 3. That's 5/2, 2.5. Which of those black integers can you get closest to the red one there? 2. So the greatest integer function value of 2.5 is accepted as 2. Now guys, notice these answers coming out can be found there. The original numbers I can't find. I'm going to try another one here. Number 4. Some markers here. Let's try this greatest integer function value of, let's try one here, -1/2. -1/2 is not in the original set, but I know where it's located. It's located, see if I'm correct here, guys, is it located here between -1 and 0. Now, what's the closest you can get to it and not go over? It's got to be less than.
-1.
I heard it, -1. Look at those strange answers coming out. But these answers, -1, 0, 0, 2, what else did I have here? It's all I had there. All these are integers. So they're asking for an integer to come out of that set for that number. Let's try another one here, number 5. Let's try greatest integer function value at, guys, here goes. I'm going to try -7/2. Which is not in the original set. That's a -3 1/2. Guys, -3 1/2 is going to fall right in here. I'll call it 7/2. Now, based on what we're describing here, what do you think the answer is? What's the closest I can get to negative 3.5 and not go over?
-4.
It is negative 4. Negative 4 is as close as you can get to it. Negative 4 will be right after that negative 3. And that's the way it works. And these answers again, this, and others that I may do, are all located in that set of integers. And this description says find the greatest integer function. Now that's a description. What does the graph look like now? I don't have the graph for this. I have the graph for the others. I don't have a graph to look at. Is it going to be a circle? No. The circle wouldn't be a function to begin with. It wouldn't pass the vertical line test. Straight line? I doubt it. A parabola? No, it's not going to be a parabola. So let's plot these and see what this strange one is going to look like. Strangest of all the functions. Here we go, guys. I'll plot a few points. We said earlier the greatest integer function's value at 1/2 is 0. That means, over here on my grid, I have a point right there caught between 0 and 1. At 1/2, I'm supposed to be at 0. We said also at 3/4, I'm supposed to be at 0. Now 3/4 is a little bit closer to 1, but I stay right on the x-axis at 0. In here. That's squeezed in there. So guys, these two are the same value there. Now, can anyone tell me based on that, do you think all those little fractions caught between 0 and 1 are going to stay right at 0? 1/2 did, 3/4 did. You think 5/6 would? You think if I ask you to find the greatest integer function at 5/6, do you think I'll get 0 again? Is 0 the closest one? It is. 5/6 back here is also caught between, and here somewhere, it's caught, these markers are not working today. 5/6 is caught between 0 and 1. So let me point this out. It's in here somewhere. 5/6. And again, 0 is the closest you can get to it. So all these numbers are staying right at 0, in fact 0 itself, until I reach 1. I'm placing an open circle there for a reason. Someone tell me, what do you think the greatest integer function at 1 would be? Not 1/2, not 1/3, just 1. And I know where 1 is. Is 1 in the set to begin with? Is it in the original set of integers? And therefore, no looking, no location, it is 1 for sure. It's there now. Let me ask you this. What do you think the greatest integer function value at, we'll call it 1 1/2. You'll say, Professor, it's not in the original black set of integers, but I know in real life where it is, it's caught between 1 and 2. This is 1 1/2. Guys, which one is closest to 1 1/2 in the black set of integers? Is 1 still the closest you can get to 1 1/2 and not go over? If you go over, you're into a 2, not go over. So 1 again. What does that tell me? When I reach 1, it jumps up to 1. Look at this strange graph. Stays there until you reach 2. Now what do you think the greatest integer function value at 2 is when I finally reach 2? Is it in the original set of integers? So I don't have to try to locate it. It's in there now. So it is 2. So this is going to jump up to 2. And it stays there until you reach 3. Then jumps up to 3. It stays there and continues like that forever. Looks like a little series of steps. Now the other side, if you think about what's going on here, guys, I've got this closed in already at 0. 0 is in the original set. Then we'll place an open circle here, close in at -1, -1, and show another little step on the left. If I want to show another little step here, open here, close this in, and all these stay at -2. And it continues like that. And sometimes I'll call this the step function, the greatest integer function. Strangest function of all the parent functions. Okay, but just in case we see it. Let me step back. Did it sort of make sense the way I described it? We're looking at the original black set of integers, hoping that it's there. So if I ask you what is the greatest integer function's value at 100, is 100 in the original black set of integers to begin with? So the answer is 100. Now, I'll throw this at you. What's the greatest integer function's value at 99.5? 99. Try to get as close to that number that I gave you and not go over. Okay, and the answer coming out also must also be an integer. Guys, strange looking graph. Series of little steps here. Now, since I've talked about this, before I jump into what I wanted to do here, can anyone tell me this strange graph? Can anyone tell me from left to right along the x-axis, this direction, what do you think is implied to be the set of x's that are being used called the domain? What will I accept as the domain of this strange greatest integer function? From left to right. Are there some breaks on my graph? So if I'm going from left to right, I'm going from left to right, not up and down yet, that's range. I'm just looking at it from left to right. As I go from left to right, you'll say, Professor, I see that little step there, but then there's a hole there. But is that hole being picked up here? All of a sudden jumps and picks up at there. It's closed in, then travels to another little break, but then all of a sudden jumps and includes it. So what do you think the numbers are being used along that x-axis for my domain? Is it everything being used? All real numbers? In fact, did I use some real numbers? By the way, this is x here. I used for my x, look at these x values I had for examples. And I threw in this, and I threw in that, and I threw in that. I threw in some fractions, I threw in zero, whole numbers. Therefore, my domain here is open. You may replace x inside there with anything you wish. That's my domain. Now the question is, I think I saw a student will give me this answer, what do you think the up and down is? That's the range of the graph. Does anyone think they know what the range would be described as? And that's not all real numbers. I'll tell you ahead of time. Yeah, I saw a hand going up. Yes?
No, I was gonna say all real numbers.
Not all real numbers. Oh, by the way, let me tell you what the output is, the range. My range right now is this in my examples. Now, tell me, you might be able to tell me from my examples, what type of numbers, these are the range numbers. What type of numbers are these? Give me a good description. What's coming out? That's my range. Integers. It's coming out to be one of these. So therefore, my range is, and I'd like to use this z here, is a set of integers. That's my range. Coming out. So you can replace x, guys, inside here by anything you wish, which we said all real numbers. Where am I? Right here. This x. But guarantee if you do, the output, what's coming out must be inside this set. And that set is called the integers. That's your range. Now, before I close it down, because it's so strange, can anyone tell me, what do you think this would be if you saw it? The greatest integer function value of pi. I see hands going up right quickly. Yes?
It's
3. Pi is roughly what, 3.14? And you know 3.14 is not in this original set. So she says, Professor, the closest I can get to 3.14 is 3. Let's try one more. But you guys told me inside here I can replace x by any number I wish. How about square root 2? It's not inside this set. What's the closest I can get to it? What do you think the answer is? The greatest integer function's value at radical 2. Go for it.
I'm gonna go 1.
It is 1. Tell the class why you said 1. And by the way, 1's in here, right here it is.
Time 1 point something.
Tell me again.
1 point something.
It is? Beautiful. Square root 2 is 1 point something. So he says the closest I get, Professor, inside that set you gave me of integers is 1. And that's the way it works. So I thought I'd get that out of the way. Mr. Parker, when I had you guys in class, I don't think I showed you this one. the greatest integer function because it is so strange. But just in case it comes up. Did you see it in Math 7 or Math 8?
No, I saw it in Korea, and that was it.
Oh, you didn't see it? Okay. Oh, you saw it there, though?
Yeah, I saw it. in
Okay,
Korea.
okay. So it does come up, so just in case. Now, with all that said, let's get down to where we need to be, what we should be looking at. Let me check out these markers here. What on earth if, and I realize this is a strange graph itself, but suppose, Professor, they get even stranger. And maybe you don't accept them as a parent graph, it's just a graph. And you've got questions here about this. Okay, let's go into part 3. Try these markers here. Okay, guys, just roughly, I didn't bring my straight edge with me today to draw all these straight. Let's make a rough sketch here. Let's go to the X and Y axis, a grid. Here goes. And let's place on this grid not one of the parent graphs. Something may look a little different. Now bear with me. I'm gonna plot a few points. -1, -2, -3. I'm squeezing that in, guys, out to a -4. It goes on forever, of course. On the other side, we'll try these numbers out to +4. Y-axis, I'm going to go up to, we'll try 5. And let's drop down, just in case I need them, try a few numbers down here on the Y-axis. And I'll drop down to a -4, of course it goes forever. Just try and get the grid ready for me. Now we'll plot a few points, and then we'll connect. So guys, for basic algebra, if I start plotting points, let's start out with -4 up 3, and I will label this for you. So this blue might work. -4 up 3, standing where I am right here, it looks like it's right in there. And we'll place on the side here, I want that to represent -4, 3. Trying to think of a nice graph here to give us something to work with here. Beautiful. Now I'm going to place a point at -1, 0. I'm now going to go out to 2, down 2. And I'll label that right there with coordinates. Just plotting points. Let's go up to 3, 0 on the x-axis. And let's try the last one to be out 4, up 5. We all know how to plot points here. Now it looks like I'm going to make a different shape here. Let me throw in one more point. We'll go out to the left just a little, out here. And we'll go out to a -5. And then plot that to show you what my graph may look like. Go out -5, plot the point. Now we'll connect this from left to right. Here goes. Make sure I got a good markers so you guys can see this. I'm connecting this manner. Up this way, comes down, picks up this point, comes on down. I'm going to have to go through -1 on the y-axis, picks that point up, turns, gradually turns, picks up 3, and goes on up to that point there, 4 or 5. And in fact, I think I'm going to have this side to go a little further, just on up like this, like it's going forever. And let's say the graph looks something like that. Not one of the parent functions. Just plotted a few points, connected, and I hope you guys can see it. If you can't, let me know. And then we look at it like that. Now, by the way, first, is this the graph of a function?
Yes.
Does it pass the vertical line test? If I pass a vertical line where I wish, it's one point of intersection, it's a function. So we'll call this a function. I'm not going to give a name to it. Let's call it f of x. Now, some vocabulary. Number 1, we like to, in mathematics, use this word for a function. What are this function's zeros? Can someone tell me what you think I'm looking at if I'm staring at a graph? What on earth do you think I'm looking at for them to, or for me to answer that question? What are the zeros? Okay, guys, go for it.
The intercepts?
Which intercepts?
X.
The x-intercepts, that's all it is. So say, please go to your graph, if you have the graph, and he tells me, Professor, just pick up the x-intercepts. Now, does my graph, strange looking graph, have any x-intercepts? Does it touch the x-axis or cross through the x-axis? Yes, I see -5, -1, and 3. So guys, on the side here, -5, -1, 3. Those are called the zeros. They are the x-intercepts. That's all it comes down to, just the x-intercept. Vocabulary. Number 2. Now they're going to ask me to look at this strange graph, and from calculus, answer this question. Where is this graph increasing? And you look at it from left to right. So you're going to tell me in interval notation which pieces of this graph are rising as I go from left to right. And I see hands going up. Yes?
-5 to -4.
Okay, hang on now. So she says, Professor, this piece right here from left to right as I travel is rising. And she's going to describe that as from -5 over to -4. Right here. Beautiful. Katie, is there any other spot here that you would assume from left to right as I travel along that blue graph, it's rising again?
From 2 to 4.
Okay, from here to, now, is this piece right here rising? Guys, help me out. Is all that rising forever? How would you describe that? 2 through infinity. That's just a union. I like the union symbol. 2 through infinity. I think those are the only 2 places I see where it's rising as you go from left to right. Increasing, we've got that out of the way. Katie, thank you. Now decreasing. Where from left to right, as you go from this, on the graph from left to right, where on earth is it falling? Well, it looks like it's going to pick up here and fall, keeps falling until it reaches that transition point. Now, in what interval from left to right is that happening? It looks like from, help me out guys, -4 over to 2. So increasing, decreasing. Got that out of the way. Yes, go ahead.
I had a question. How do you know that it starts at -5? So why isn't it like -infinity until?
Beautiful, 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 beautiful. Question. Got you. I didn't do this. I did not, I stopped it right there.
Oh, okay.
If I did this, I don't understand what you're saying. If I had done this, which I didn't, that would have meant it goes on forever. I didn't do that. I stopped this one for a reason at -5. Was that your question?
Yeah, thanks.
Okay. Increasing, decreasing. Number 3. Now they're asking you to look at this strange graph and come up with answers for these. Are there some high points on this graph? What you would describe as high points on the graph. Well, it looks like there's a high point right here. Before I start answering questions here, is that the highest of all points on the entire graph? No, because this is implied it does what? It goes forever. Is there maybe a low point somewhere on the graph? It looks like right in here might be a low point. Now, as I take a close look at it, is this the lowest point on the entire graph? Okay, so that low point there is also the lowest of all. Back to that max, this is the max right here, the highest, but it's not the highest of all. And that can happen. So my vocabulary to distinguish is this. they may ask you to find the local maximum. And guys, really they just need that y coordinate, but if you want to name the entire point, go for it. The local maximum right here in that locality, -4, 3. Is that acting as a local maximum? Is that the highest point in that locality? I'm gonna just say 3. That's the highest. I think that's the only one I see. It could have more than one. This one just has one. Now, there also is a local minimum point. Easily seen for your exam, the next exam, you'll have one of these. Local minimum, right here, it's a low point. It's right in that vicinity right there. And guys, I see it's 2, -2. I'm just name it with the y coordinate. It's -2. That's considered my local minimum point. Now, number 4, if. When you start comparing the max and the min, you might end up with this. More vocabulary. Is there something called the absolute maximum? Now, if they use the word absolute, now they want you to name the highest of all, if it exists. Guys, on this graph, is there a point that you would identify as being higher than everything? Cannot do it. Why? This goes forever. There's no high point. It keeps going. So therefore, in this case, there is none. Sometimes there is. Now, might there be an absolute minimum point? And I'll describe that to you. Is there a point on this graph that you would say, Professor, it's the lowest of all points? And it looks like right here is at the lowest point on the graph altogether. And therefore the y coordinate, I just need the y coordinate. The absolute minimum is -2. Local max, local min, absolute max, absolute min, increasing, decreasing. Mr. Park, what else should I list besides that? What else are you guys in the calc classes concerned about? Do you think of anything else I should ask the class?
Inflection point?
Okay, well, the inflection points, I better leave that for calc. Anything else?
No.
Okay. Number 5. What on earth is this function's domain? And I did not name the function for you. I showed you this graph. So I'm looking for the axis from left to right. Tell me a good way to describe this graph incorporates what from left to right along the x-axis? From what to what? I see hands going up.
Bracket, -5 to
Hang on now. Bracket, -5. I'll take that. And she tells me what? Through infinity. From left to right. I agree. Range. On this strange graph that does represent a function. Now be careful. Now I'm looking at the up and down. The y values along the y-axis. Guys, along the y-axis, I think it drops down to a low of, for a y, -2. How high up does it go? Infinity. So I got what? Bracket again, -2 through infinity. So there's my domain, my range, increasing, decreasing, local max, local min, absolute max, absolute min. Mr. Park, I think maybe that might be it. Now we'll point this out. I'm not going to have you guys be responsible for this. For an example, this was rising in the blue, and it started falling. It transitioned from one to the other. As soon as it transitions, in this case, I end up with what? A local max. Now, what type of transition was taking place? It was rising on the left and falling on the right. That will make a max show up. I had a min here on the left of it, it was falling in the red. Move to the right of it, it's rising. So if I go from what? Falling to rising, I have a minimum. They call those the transition points. or local max, local min. See what else should I point out here? Ah, yes, yes, yes. Please tell me, as I move along this way, look at this. Is my graph bending down from here? This little piece right here. Is it actually not just increasing, decreasing? Is it bending down? And is this little piece right here, this piece right here, is that bending up? In other words, they described in calculus, this would not hold water. If you poured water there, this would hold water. So this right, it doesn't hold water or not. That's another characteristic that they'll have in calculus. But guys, right now for us, I think basically that's it. Now, who would like to, yes, Katie?
I just have a question. Why, for the increasing and decreasing values, do you use the x values, and then for the local max and minimum, use the y values?
Okay, on the local, hang on now, local min, local max. Okay, that's beautiful. If I say what's the maximum, please tell me. If I say what's the highest point on a graph, guys, do you think about the y, how high up it goes? That's why we use the y value. Okay, if I ask you for the, what, minimum, local minimum point, I'm looking for the y value. How far down does it drop? And that, again, is the y value. Beautiful. Then you're saying, okay, here, you did this along the x-axis. They describe this part as along the x-axis. Okay, but these others are the y values. Good question, though. I see what you're saying there. Yes?
So for the second part, increasing and decreasing.
Yes.
What, do we not use open and closed-ended brackets?
Beautiful, beautiful. Now, your textbook. Someone asked this last week. Someone must be doing their homework. They asked me last week. They said, Professor, would you count wrong if I did this? I think your textbook does put them in brackets. I don't like it. Wonder why I would not like it if I asked you for when is it increasing, and we said from -5 over to a -4, Professor. What's it doing at -5? At the very beginning, at the -5 of that integral, is it doing anything at all? Is that just a stationary point? That's where it starts? So I prefer this myself. This is doing nothing. And then -4, by the time you reach this point right here, is it stopping? By the time you reach this point, has it become stationary? It's just stopped? Then it picks up and starts falling. So at that top point, is it really included as increasing? No, it's not increasing, it's stopped. So this is initial, this is the ending, and there's the stationary points. Your book, though, I think for some reason, I don't like that, they did allow students to put brackets, so I would not count that wrong. You did. He had a good question. I prefer it like that myself. Good question, though. Absolutely. Guys, anything else? Now, Mr. Park, the last thing on this. That's why I was asking you a question here. Number 7. Anyone describe an interval notation? I got to be careful myself here if I gave you enough information. I think I did. Where is this function guaranteed to be that? Now let me describe first what I want. I didn't name the function for you. I didn't name it f of x equals x squared plus 3x plus whatever. I didn't name it. Just a graph. I would know where on earth for the x's that I'm guaranteed if you replace x into that function, the result is negative. Where are those x's located? If I should place them in my function, I'm guaranteed the answer is going to come out to be negative, even though I don't even have the function in front of me to plug in. I just have this graph. Go for it.
-1. So
Beautiful. Hang on. Beautiful. Hang on. Let's see if I can use this green marker. It'll work for me. You're saying from -1. Tell me more.
2 until 3.
Look at that. He said, Professor, all that little piece right there is below the x-axis. Isn't it? Is all that below the x-axis? If I'm below the x-axis, that represents negative. I'm in the negative territory down there. And this is what I wanted here. I want something negative, less than 0. So he described this as -1 out to, what was it, 3?
Yeah.
And I agree 100%. Now let's answer this. Where am I guaranteed for the x's if this will be true? The function is, let's put greater than or equal to this time. 0. And I don't have the function to plug in numbers. It's a graph. So what are you going to look at on the graph to answer that question? When is my function greater than or equal to positive 0? I guess it's hang on up again. Just kidding. Yeah. Go ahead. Oh, hold on now. Hold on. Let me do it like this. This is my graph. You tell me all this. Look at this. Is all that from -5 over to a -1, is all that above the x-axis? Is that true? Just that little piece there. Is all that above the x-axis? That's positive. Now she's telling me, hold on, professor, there's another piece. Look at this. 3 through infinity. All that's above the x-axis. Representing positive if you're above the x-axis. Therefore, to answer this, with her help, it's -5 to a -1. And by the way, I see a bracket here coming up. -5 to a -1 union. And she also said, professor, from 3, I think it was, through infinity. Yes or no? Now, could you do something like that for me? Not on the quiz Wednesday. The quiz on Wednesday is a gift. It's a gift. He's already brought the handout to me. I'll get the handout to you here in just a few minutes. What that may look like. It's the next exam. If I have a graph on there, I'll draw the graph for you and ask you these questions. Now, could you take a graph and answer those questions for me? Of course you could. Is that true? Now, looking at this, guys, I don't think I see anything else. Mr. Park, with all that mathematics you have, tell the class, since many of my students will be moving on and probably be the top students in their calc class when they get there. Tell the class what if I gave them, hang on, I don't want to put you on the spot. Suppose I gave them the function, I named it for you, I did not give a graph. This time I was nice, I gave you the function. Like you saw in the exam. I actually named the function. But I did not show you its picture, its graph. And then I asked you the same questions. Without a graph. That's calculus. Mr. Park. What would they have to do now to answer those same questions, but there's no graph there?
We find the roots and then we take the derivative.
Hang on now. So you're telling me I can find what I call zeros, the x-intercepts, by doing what?
Factoring.
Okay, first one, set this equal to 0. Guys, look at this now. I just created this real quickly. May not be nice. You set equal to 0. By the way, were these points earlier, by zeros, where were they? My goodness, up here. These x-intercepts, were they at 0? And therefore, if the function's given to you in function form, and it's not the picture, it's the graph, what are you going to do to find the zeros? He says set it equal to 0 and solve it. Now this one may not be nice. I don't know, I've created this real quickly. Did I factor that correctly? Okay. Now, I don't think, since I created this so quickly, I don't think this one factors. Does it?
No.
What you have to do, use quadratic formula. Which I think, I'm doing my math in my head here, I think it's going to work out. And if you use the quadratic formula on this and finish it up, you'll find the 3 zeros without actually seeing the graph. You'll know where the x-intercepts are quickly, without even looking at the graph. So that's one way. But what I want him to answer now, though, for me is, do you remember in calc, Mr. Park, sure you do, how can they find where it's increasing, decreasing, local max, local min, and all that business, and they don't have a sketch to look at? What does one do in calculus to do that without the graph?
We find the derivative function.
There you go, the key, what was that word?
Derivative.
Derivative, derivative, derivative. So one part of calculus is just doing derivatives. And you don't even know what a derivative right now is, but one whole part of the course is just take the derivative. And if you did, that would help you to find these answers without having this to look at. I thought I would just bring that in. Of course, I'm not going to ask you to do that here, no. But you have no clue as to what to do with the derivative here. The graph will be provided to you. Guys, take a close look. Any concerns there at all? Okay, I thought I'd get that out of the way first. Now, that said, Kyle, I have not forgotten you. Here goes. Don't try to incorporate this on that strange graph. As I look at the graph, hang on guys, please tell me, let's see if I can make this look nice. That graph is all messed up there with different colors. If, Kyle, here goes. He was asking about this last week. If they should give me on this function a point, let's say the point falls right here. I'll make it darker right there. And then I'm going to end another point with another point, end here. And they asked me to please take a close look at the travel from this initial point to get to this point and stay on that curve. So please tell me, as I stay on the curve and I start moving from this initial point, will I first go up, so I'm increasing, then all of a sudden I do what? I drop down to that point, then I pick up and do what? Increase again until I reach my destination. Are there some changes in my motion there as I move from one point to the other? Yeah, we go up, increasing for a while, and all of a sudden drop. That's a change. Then increase again, that's another change. There's some changes taking place. Now they're going to ask us something about that change. Now, is the change constant? No. So your book gives it like this, or gives a name to it. They call it the average rate of change. All this coming up on your next exam. You'll say, wait, Professor, I can barely do a quadratic formula. Now you're going to ask me to do something called average rate of change? Come on now. That's the course. So they're going to ask you, on the average, what changes are taking place? And you guys have already said, Francie, right here, there's some changes taking place. If you want to go from this initial to this destination and you stay on that curve, some parts are increasing, some parts are decreasing, there's changes taking place. They want to know what the average rate of change is. Now, I love this. Can anyone tell me what do you think I'll reflect to find the average rate of change? And maybe I should ask you to reflect all the way back to middle school, where they may have not used that phrase rate of change back then. Can anyone tell me what back in middle school did you find that found the change on a straight line back then? You guys just said it was straight lines, I'm assuming back then. There was something the teacher showed you how to do, you did it, you may not have known what all it was all about, but you knew how to find it. Does anyone remember what it was? Back then, usually on a straight line, they would draw a straight line like this back in middle school. I've seen many middle school teachers do this. They'll draw a line, and they'll ask students to find something about that line. Which, thank you, the slope. And this letter was referencing slope. And how does one find the slope?
Y equals mx plus b.
Oh, that's beautiful. That's the name of the equation for the line. What's the slope itself?
Yeah, right.
Does anyone know what you were finding when you found the slope? What was it?
Rise over run.
Rise over run. Some teachers would describe it like this: rise over run. But even on mine, it's rising in certain places and it's falling, so some changes taking place. But they described it back then as what? Rise over run Or I prefer this, change in y, delta y, over delta x. Change in y over change in x. And that was a slope. You may have seen it for the change in y, written like this. y1 subtract y2 over x1 subtract x2. I think most textbooks give this as a standard slope formula. Subtract the y's, that's the change in the y's, delta y. Find the difference in the x's, that's delta x, change in the x's, and you have slope. You say, Professor, are you kidding? Are we going to use slope on here? On this? That's not a straight line. Back in middle school, I could find the slope of a straight line. You give me 2 points, I could find it. Now, there's something about slope here. Here goes. I'm going to connect. I will connect these 2 points with a straight line. And guess what they allow us to do for the average rate of change as I go from the initial point to that destination, all those changes taking place along the curve, guess what they let us accept as the average change, rate of change? The slope of the straight line connecting those 2 points. So if I can go back to middle school, take those 2 points, and find the slope with delta y over delta x, they let you accept that as the average rate of change on this strange curve as you move from that point to the other point. So guys, I need to find, in my case, from negative 4, 3, I think it was, wasn't it? Is it negative 4, 3? I think it was. Negative 4, 3, out to, my destination was, help me out, 4 or 5. Are those the 2 points I had concerns about? Was that my initial and my destination? Yeah. Go back to middle school and find the slope. That's all they want. Find the slope connecting those two. That straight line. Guys, I'm going to use this formula. Y1 subtract y2 over x1 minus x2. I'm going to label my first point as x1, y1. Second point, x2, y2. What's my time here? It's almost time for a break here. I'll finish this up. I'm going to label mine like this and then apply this formula. So guys, my slope here would be y1 subtract y2, the way mine labeled would be 3 subtract 5. x1 subtract x2, negative 4 subtract 4. I'm going to end up with negative 2 over a negative 8, reduced down to 1/4. I hope I didn't make a mistake. I did it quickly. Is it 1/4, guys? They let you accept that as, now look at this. That's the average rate of change, 1/4, as you travel from this point to this point. It's nothing but the slope of that line connecting the two. That's going to be accepted as the average rate of change of that entire function from one point to the other. It just comes down to slope. Now, before I do close down, I heard a student tell me this earlier. They will also ask you to write the equation of that line. And by the way, guys, a line that connects 2 points on a curve, for us, it's called a secant line. So they're going to ask you to find the equation of the secant line. That's just a word they give, vocabulary for a line connecting 2 points on a curve, secant line. Equation for a secant line, I'm going to turn to what? Mx plus b? I heard that. By the way, I prefer another form though before I get to mx plus b. Does anyone remember another form if they ask you to write the equation of a straight line? Does anyone recall, maybe from middle school, there was another form that sometimes is easier to work with, even though I am going to write the answer in the mx plus b form though. Does anyone recall? We need to have a field trip. We need to make a trip across the street. I know some of those teachers teach in middle school. Wouldn't it be exciting to go over on campus and see what they're doing? Let's see if they're doing equations of lines over there. I think they are. Does anyone recall another form I could take besides mx plus b? I like this one. It's called point slope. Looks like this. And then we're going to take a break after this. It's called point slope form. And they just want you to know what it looks like and then plug in numbers. And you'll have the equation for that straight line over there that connects those 2 points. Guys, the way mine is labeled, it'll be y subtract y1. I label y1, this is my choice, 3. We'll put a 3 here. Slope, we calculate the slope. We got a 1/4. And then x subtract a -4. I'll put that in carefully. So that's my x1, y1 from over there. Put in, clean this up. I got y subtract 3, 1/4. Guys, looks like inside there is x plus 4. Now, since he mentioned, one of my students mentioned, Professor, I remember it as an mx plus b. I can place this in the mx plus b form. In other words, get y by itself. Just do this, y subtract 3. Use the distributive property. And guys, I think you end up with 1/4 of 4 is 1. Move that 3 over to get the y by itself. Just doing some algebra here. And I think, if I have no mistake, please tell me, I think, is that it? If there's no mistake. Mr. Park, there's no mistake, is there? Okay. So this is in the form of slope intercept. mx plus b. And that's the equation of that line over there. What's the average rate of change? The slope, 1/4. So that's where slope comes in, and then also for average rate of change. Is that making sense the way we presented it? Okay, let's find 2 points, connect, and find the slope. Okay. Now, this says, Professor, it's time for a break. It is time for a break. I'm thinking about doing something with you guys today. We're going to see if it works. Mr. Park, it may not be today, I'm thinking about though. Eventually we're going to have to start doing this. We'll have to take the last 30 minutes of class on a few days to go down to the math lab and do some group work. Me standing here just lecturing, and I'm good. I make sense of all this. I'm good. But it may make more sense if you're with others at a table and you have a handout that's going to be turned in and you're working on it together. So I might try that today. What do you guys think? Maybe the last 30 minutes of class, which is going to cut it down short because I'm going down with you. Okay? And that means as a group, I've done group work before, you got to focus, and some of us do not know, we don't know each other. Some of us know, some you'll meet other students. And I don't know exactly how to pair you up right now. I'll probably see how many tables are down there. Mr. Park, there's quite a few tables, right?
Mm-hmm.
And I'm sure the math lab is probably empty, not too busy right now. I would not think it's busy, I don't know. Right?
It's quite busy.
Oh, is it busy?
Yeah.
So I may send you down first and see how busy it is.
Okay.
And then we'll think about it. So guys, I'm thinking about that. I think that would help. And then give you a few points for the group work. So you get a few points for the group work. So if that happens, I might try it with what he made copies of for the quiz Wednesday. Just give you a copy in your little group, let you work it out, discuss it, and then turn it in to me, and then I'll give you a few points for what I will call group work. Now, how many points? 100? 50? No. 2? Maybe. It'll be a minimal number of points. It'll be help a little bit for group work. So guys, I think we'll try that. I'm going to check downstairs and see how busy it is. It's not that busy today. We may try that the last 30 minutes of class. Okay, now, we've done so much. I'll see you in about 10 minutes.